Why is it so hard to reach Mars? Aside from Earth, Mars stands out as the planet with relatively favorable conditions for human. Space agencies like NASA, along with private companies like SpaceX, are already sketching out plans to send the next generation of astronauts to the Red Planet, but so far nobody has managed to accomplish that mission. Back in the 1960s space race, NASA conducted 6 crewed missions to the Moon, placing a total of 12 astronauts on the surface of our natural satellite. It's tempting to think that sending humans to Mars should be easy now, especially when we remember that we went to the Moon repeatedly almost 5 decades ago, and today astronauts seem to travel to space quite regularly, spending long periods on the International Space Station. However, even in 2025, achieving the feat of placing the first humans on Martian soil still seems distant. Science and technology show that sending a crew to Mars is a challenge of extraordinary proportions, far beyond anything we've done in the history of space exploration. The main reason lies in the massive distance between Earth and Mars. Mars really is extremely far away. We often think of space travel as going to distant places because we see astronauts going to the ISS quite frequently. For years, Russian cosmonauts also headed to the station in Soyuz spacecraft, and nowadays Chinese TA go to the Tiangong space station. However, keep in mind that these spacecraft and stations orbit Earth just a few hundred kilometers up. The International Space Station, for example, is about 250 miles above the Earth's surface. That's roughly the distance from Las Vegas to Phoenix. This region is part of what we call low Earth orbit (LEO). Crewed missions to the Moon go beyond low Earth orbit because our satellite orbits Earth at an average distance of 236,000 miles, about 1,000 times higher than LEO. On the Apollo missions, the trip to the Moon took about 3 days. But aiming for Mars makes things much more complex. Instead of traveling in a geocentric orbit around Earth, you switch to a heliocentric orbit around the Sun. This involves unimaginably larger distances. The separation between Earth and Mars varies, but the closest approach is around 34 million miles and happens every 26 months when the two planets align in a more favorable way. At other times the distance can be much greater, far more than the distance to the Moon and about 1 million times the distance to the ISS. These numbers already show the huge difficulty without even going into propulsion and orbital dynamics in detail. To clarify, let's compare in a broad way 2 crewed missions using approximate data: one around Earth, a single crew member, and another to the Moon, 3 members, in the early 60s. Mercury 6 with John Glenn used an Atlas rocket of 120 tons and about 95 foot tall, carrying only 1.2 tons. The Mercury capsule to an altitude of 124 miles. It was a flight with 1 astronaut and lasted about 5 hours. Now looking at a lunar mission around 1,000 times farther, we can see a big leap. Apollo 17, the last crewed mission to the Moon, transported a command and service module plus a lunar module, together weighing about 50 tons. These were launched by the gigantic Saturn V, weighing around 3,000 tons and standing 360 feet tall. That mission lasted about 12.5 days. 2 astronauts landed on the Moon and stayed a little over 3 days, while a third remained in lunar orbit waiting for them to come back. Comparing a typical trip to low Earth orbit with one to the Moon highlights the huge difference in scale. Payload mass grows from 1.2 tons to 50, and the rocket mass grows from 120 to 3,000 tons. Now imagine a trip to Mars. It would be even bigger. For instance, in one proposed mission for 2027 with 6 astronauts, calculations show it would take 174 days to get there and 2011 to return, plus 539 days on Mars, a total of about 911 days over 2.5 years. They'd need a long stay on the Red Planet to wait for the orbital configuration that minimizes the fuel needed to get back. The jump from the Moon's distance to Mars's distance is enormous, but that's not all. Compared to a 12-day lunar mission with 3 astronauts, a 2.5-year journey with 6 crew members would require about 150 times more supplies, because in addition to doubling the crew, the trip lasts 73 times longer. At the same time, more radiation protection would be needed since the interplanet flight would last much longer, and that calls for adding protective materials or special shielding which increases the spacecraft's mass and still isn't fully solved. There's also concern about wear and tear on equipment over all that time. If anything fails, you can't send spare parts right away like on the ISS. Everything would have to be on board, which adds even more weight. Transporting so much mass requires huge amounts of fuel. You need propellant to accelerate toward Mars, slow down once you arrive, and then make the trip back. That could mean hundreds of tons of fuel. Some scientists imagine obtaining this fuel from minerals or gases found under the Martian surface, but no extraction or processing system has been tested in real operations until proven otherwise. The only reliable way is to take all the fuel from Earth. As a result, estimates suggest that somewhere between 850 and 1,250 tons of propellant would be needed for the round trip. For comparison, the International Space Station weighs about 420 tons. The old Space Shuttle could carry about 15 to 25 tons. To low Earth orbit rockets like Ariane 5 or the Russian Proton can place around 20 tons into LEO. Starship, when fully operational, aims to carry up to 200 tons, a remarkable leap. Still, even the most powerful rockets would need multiple launches to send all the necessary infrastructure into orbit. Likely there would be several flights to deploy propulsion modules, supplies, living quarters, and cargo ships. Only after assembling everything in orbit could the crewed spacecraft be launched. Remember that during the entire Apollo program, the Saturn V was used in just 9 crewed launches to the Moon. It could take just over 120 tons to LEO and 50 to the Moon. Some believe NASA's new SLS might match or exceed the Saturn V's performance, but you'd still need multiple launches for a single Mars mission. Another big dilemma is the extended absence of gravity. Spending about 539 days in microgravity has profound effects on the human body. We don't yet have spacecraft like those in sci-fi movies with large rotating cylinders to simulate gravity by spinning. That means the crew would spend nearly all their time in zero gravity, and we don't really know if they'd be fit to walk on Mars after so long. Then there are psychological factors. 2.5 years is a very long time to be stuck in a cramped space under high stress with no fluid conversations with family or friends on Earth due to communication delays. Even at the speed of light, radio messages can take around 8 minutes to go back and forth, making real-time chats impossible. Once on Mars, astronauts would still have to cope with harsh conditions, staying in pressurized environments around the clock, maybe in compartments even smaller than the spacecraft that carried them there. Some enthusiasts and optimists say our current technology is enough, we just lack the will and the funds to pull off this interplanetary journey, but from a scientific point of view, we're not quite that ready. The practical, technological, and health issues are significant. Even so, with the right determination, funding, and planning, we may reach Mars in the coming decades. NASA believes that with today's advancements, we might send the first humans to Mars before the end of this century. Others say there is still a lot to be developed. While the most optimistic folks offer shorter timelines, like Elon Musk, who has stated he wants to send humans to Mars by the end of this decade. What do you think? Are we headed to Mars soon, or will humanity never reach another celestial body? Share your thoughts in the comments.